Hi students, in last video we discussed about elimination method. Today we are going to start penalty approach method. So here we have one problem. Consider the bar shown in figure. An axial load P 200 into 10 raised to 3 Newton is applied as shown in figure using penalty approach method for handling boundary condition. Do the following. First we have to calculate, determine the nodal displacement, determine the stress in each element, determine the reaction forces. Here we have the first part is aluminum and second part is steel, and it is fixed at both the ends, and this is the direction. Here we have the point P, that is load P. The first is the length is 300 mm and the second part is 400 mm. Area 1 is area of this aluminum bar is 2400 mm square, and Young's modulus is 70 into 10 raised to 4 Newton per meter square. Here we have to convert this into Newton per mm square. Okay, and area of the second bar is 600 mm square, and Young's modulus is 200 into 10 raised to 9 Newton per meter square. Again here we have to convert this into Newton per mm square. So before going to start the solving of this problem, I will tell you what is penalty approach method. Okay, so what we have, the basic equilibrium equation K Q F. This is global stiffness matrix, this is global nodal displacement vector, and this is global load vector. Okay, that is indicated by K11, K12, K13, K21, K22, K23, K31, K32, K33. Okay, this is the global stiffness matrix, and here displacement Q1, Q2, Q3. This is global nodal displacement vector. This is F1, F2, F3. This is global load vector. Okay, now I will give you an example. Here it is fixed, and here we have one stepped bar. Here we have one load. This is element 1, this is element 2. As if you consider this as fixed, then the displacement at this particular point will be 0. Okay, instead of this fixed point, I will assume here one extra element, that is spring with high stiffness. This is our bar now, this is the load, and this stiffness is C. We have to attach this spring which has high stiffness, so that at this particular point, I mean in this fixed point, the stiffness will be more. Okay, so how to calculate this C? So that C is equal to maximum of, in this matrix we have to identify the maximum value, that is Kij. Here I indicates the number of rows and J indicates number of columns. We have to substitute that value and into 10 raised to 4, so that we'll get the C value. Okay, so after getting C value, wherever we will be having the fixed point, I mean for example in this position at node 1, at Q1 we have fixed point, so we have to add this C value to this element. Okay, that is K11 plus C, and remaining as it is K12, K13, K21, K22, K23, K31, K32. Here it is free end. If it is fixed end, again we have to add that C to this K33, but here in this example that is free end, so it is K33. Then Q1, Q2, Q3 as it is. Again for load vector, here it is fixed, so I will add F1 plus A, that is displacement. Here this constant A indicates the displacement, and this is C, and this is F2, and here F3. Instead of this free end, if it is fixed, again here I will write F3 plus AC. Okay, so reaction force. Okay, reaction force, that is calculated as Ri is equal to minus C Qi minus Ai. Okay, if the displacement is equal to 0, then R is equal to minus C Q. Here we have to add this C to the corner element wherever it is fixed. Now here it is fixed at only one end, so we are adding C here. If it is fixed here also, then we have to add that C to this. Okay, so based on this, we'll see the problem now. Here we have one bar aluminium and this is the steel bar, and it is fixed at both the ends. So first we have to, what is the first step? First we have to create the FE model. Okay, so now I will create the FE model. FE model. Okay, this is the straight line. Here we have node 1, node 2 and node 3. This is 1, this is 2, this is 3. This is element 1, this is element 2. Here element 1 is aluminium, element 2 is steel. Okay, and we know the area of aluminium is 2400 mm square, and area of steel is 600 mm square, and Young's modulus for aluminium is 70 into 10 raised to 9. It is 70 into 10 raised to 9 Newton per meter square. We have to convert this into mm square. 70 into 10 raised to 3 Newton per mm square. Again here Young's modulus for steel, that is 200 into 10 raised to 9 Newton per mm square. This is 10 raised to 5. After conversion we get 10 raised to 5. Okay, so now here we have Q1, here we have Q2, here we have Q3, and here the F1, that is equal to 0, here F2 again that is equal to 0, but here we have, that is P, that load is P, and it is given by P is equal to 200 into 10 raised to 3 Newton, and length from here to here, the length is 300 mm, and from here to here the length is 400 mm, so that this is L1 and this is L2. So this is the given data. Now I will create stiffness matrix. Stiffness matrix. We know K is equal to A E by L, 1 minus 1 minus 1 1. As here we have two elements, so for element 1, K1 is equal to, what is the area? 2400 into 70 into 10 raised to 3 divided by length, that is 300, and here 1 minus 1 minus 1 1. After solving you will get K1 is equal to 10 raised to 6 outside, and inside the bracket we will get 0.56 minus 0.56 minus 0.56 0.56. Okay, similarly for element 2, that is K2, area is 600, and this is 2 into 10 raised to 5 divided by, here it is, here after conversion we get 2 into 10 raised to 5 Newton per mm square. Okay, so the length is 400, and here we have to substitute the matrix 1 minus 1 minus 1 1. Okay, so we'll get K2 is equal to 10 raised to 6 outside, inside we'll get 0.3 minus 0.3 minus 0.3 and 0.3. Now I will tell you one thing, that is, as in this problem we have two elements. For this first element it is related to Q1 and Q2, and the second element is related to Q2 and Q3. So in this, the first row indicates Q1, the second row indicates Q2. first column indicates Q1, second column indicates Q2. Similarly here the first one indicates Q2, the second one indicates Q3, and first column Q2, second column Q3. Now while writing global stiffness matrix, global stiffness matrix, that is K is equal to K1 plus K2. We have to add all the stiffness matrices. Here we have two elements, so here K is equal to, common is 10 raised to 6, 10 raised to 6. I will write it outside. Here observe this carefully. Here we have 3 rows, 3 columns, 3 rows, 3 columns. The first one is for Q1, Q2, Q3, Q1, Q2, Q3. Here in this matrix we have only Q1, Q2 values, so I will write 0.56 minus 0.56 minus 0.56. Here in this we have only Q2, Q3, Q2, Q3, Q3. So I will write it here minus 0.3, 0.3 and minus 0.3. Here in this matrix we don't have any third column that is related to Q3, and here we don't have any row which is related to Q1, so it is 0. Similarly here we don't have any Q3 value, so that is 0. Here in this, observe this carefully, here also we have Q2 row and Q2 column, here also we have Q2 row, Q2 column. So add this 0.56 and 0.3 will get 0.86. Okay, this is nothing but global stiffness matrix. Now we have to write global nodal displacement vector. Global nodal displacement vector, that is Q, Q1, Q2, Q3. Similarly, global load vector, that is F is equal to F1, F2, F3. That is equal to F1 is 0 as it is fixed end, F3 is also 0 as it is fixed end, and we know P value, that is 200 into 10 raised to 3. Now I will write equilibrium equation or equilibrium condition. Equilibrium condition, as we know, equilibrium condition, that is global stiffness matrix into global nodal displacement vector into is equal to load vector. As we know, K value 10 raised to 6, inside 0.56 minus 0.56, 0 minus 0.56, 0.86, 0.30, 0 minus 0.30 and 0.30, and this is Q1, Q2, Q3. That is equal to F1 is 0, F2 200 into 10 raised to 3, and this is 0. Okay, in last problem we know Q1 and Q3 0, we'll eliminate rows and column which is related to Q1, Q2, but here we are doing with the help of penalty approach method. So we have to calculate C value, that is applying boundary conditions Okay, so in this matrix we have to identify the larger number, that is 0.86. As I told you, C formula is maximum of Kij into 10 raised to 4. So the maximum Kij value is 0.86 into 10 raised to 6. 0.86 into 10 raised to 6, and in this formula we have 10 raised to 4. So after calculation we get C value 8.6 into 10 raised to 9 Newton per mm. This is C value. Here we have the bar like this. Here also it is fixed, here also it is fixed. here Q1, here Q2, here Q3. So we have to add this C value for this first value and the last value in this diagonal. Okay, that is for Q1 and this is for Q3. Okay, so after adding that stiffness value, we'll get global stiffness matrix. Global stiffness matrix will becomes K is equal to 10 raised to 6. This is 860056 minus 0.56, 0, 0.56, 0.86, 0.30, 0, 0.30, 8600.30. Okay, so we are adding for this and this with this C value. After adding we'll get like this. Okay, now we have to calculate global force vector. Already we have, but according to this boundary condition, global force vector changes to F is equal to F1 plus CA1, F2, F2 plus CA2, as these two are the fixed end. But here, as it is fixed end, here A1 replicates Q1, A2 replicates Q2. As Q1 is equal to 0 and Q2 is equal to 0, A1 and A2 is also 0. If 0 into anything 0, 0 into anything 0, this will become 0. So finally we will get F is equal to 0, 200 into 10 raised to 3 and 0. So finally the equilibrium condition can be written as equilibrium equation can be written as, first we have to write the K, then Q, that is equal to F. Okay, so K value 10 raised to 6, 8600.56 minus 0.56, 0, minus 0.56, 0.86, 0.30, 0, minus 0.30, 8600.30, and here Q1, Q2, Q3, and that is equal to 0, 200 into 10 raised to 3, 0. Now we have to apply the matrix multiplication so that we will get Q1, Q2, Q3. I will show you how to multiply. Okay, as per the matrix rule, we have to do the multiplication with row into column. So here first 8600.56 into 10 raised to 6 into Q1 minus 0.56 into 10 raised to 6 into Q2, that is this into this second value. First row into first column, first element into first element, second element into second element, third element into third element. Here we have 0, 0 into anything 0. So that is, I will write 0 Q3, and that is equal to the force is 0. Similarly second, minus 0.56 into 10 raised to 6 Q1 plus 0.86 into 10 raised to 6 Q2 minus 0.30 into 10 raised to 6 Q3, that is equal to 200 into 10 raised to 3. Similarly 0 into anything 0, that is 0 into Q1 minus 0.30 into 10 raised to 6 Q2, 8600.30 into Q3, that is equal to 0. Here in calculator we have direct option, that is equation. Okay, here we have total 3 unknowns. After solving these equations we will get Q1 is equal to Q2 is equal to Q3 is equal to values. Okay, so after calculation we will get Q1 as 15.1432 into 10 raised to minus 6 mm, and Q2 as 0.357 mm and 8.11265 into 10 raised to minus 6 mm. Okay, so now I will write the displacement vector, global displacement vector Q1, Q2, Q3, 15.1432 into 10 raised to minus 6, 0.2357, 8.11265 into 10 raised to minus 6, and the unit is mm. Okay, similarly we have to calculate stress in each element. Stress in each element. Here we have two elements. For sigma, what is the formula for sigma? E by L minus 1 into Qi plus 1. Here if it is Q1 Q2 or else Q2 Q3. For element 1, sigma 1 is equal to E is 70 into 10 raised to 3 divided by length is 300, so minus 1. We know Q1 value 15.1432 into 10 raised to minus 6, and Q2 is 0.2357. First we have to calculate this, and we have to multiply with minus 1, then with this plus this into 1 and this. So we'll get sigma 1 is equal to 54.2627 MPa. Okay, this is MPa, megapascal. Similarly for element 2, sigma 2 is equal to, sigma is 2 into 10 raised to 5, length is 400, minus 1, and here we have to write Q2 Q3. Q2 is 0.2357 and Q3 is 8.11265 into 10 raised to minus 6. After calculation we will get sigma 2 is equal to minus 116.2809 megapascal. Okay, and last we have to calculate the reaction force. Okay, the last one, reaction force. So here we have two fixed end, R1 and R2. So I will draw the diagram. Here it is fixed, here it is fixed. Here and here we have to calculate the reaction forces. So we have the formula Ri is equal to minus C Qi minus C. Here we have, this is Ai. The I indicates the node. So here we have to calculate for, as we have A1 and A2 is equal to 0, that is Q1 Q2 is equal to 0. Okay, so R1 becomes minus C Q1. Similarly R2, reaction 2 becomes minus C Q3. Okay, that is at node 3. So R1 is, we know C value, that is 8.6 into 10 raised to 9, and Q value is, that is for node 1, 15.1432 into 10 raised to 4. We'll get minus 130.2315 into 10 raised to 3 Newton. Similarly, reaction at node 3, minus 8.6 into 10 raised to 9, and this one Q3 value is 8.11365 into 10 raised to 4. After calculation we'll get minus 69.7687 into 10 raised to 3 Newton. So this completes the problem. So here we have the two reaction forces at node 1 and node 3, and here we have the stress in the element, that is sigma 1, and this is sigma 2, and also here we have calculated Q1, Q2, Q3. Okay, this completes the problem. In next video we will discuss some more examples. Thank you students. Bye.